Hello students, the last concept in phenomena for diffraction is that is resolving power of grating it is. So as I told in my last class, so the resolving power means the every optical instrument is having its own ability to produce distinctly separate images of two closely lying objects. The resolving power of an optical instrument is its what it is its ability to resolve two closely lying objects. Okay, so here, so each instrument is optical. Each optical instrument is having its what own resolving powers. So in the previous class we have discussed resolving dispersive power of the grating, and now so you are having what is the resolving power of what it is the grating is. So here. And one more thing, so we discussed regarding a resolving power of the what is a prism. So here the resolving power of a grating represents the what is its ability to form an separate spectral lines which are very close together. That means this grating element separates the what? Two spectral lines having certain wavelengths, so which are close together. So here also the resolving power of grating it is measured by a quantity of volts, so lambda divided by d lambda. The exact definition of this resolving power of grating is, it is again the ratio of the wavelength of the it is what is spectral lines. The wavelength of the what? Spectral lines to the smallest difference in the wavelength d lambda between this line and the what? And neighboring lines, so that the two lines appear just resolved. So that the exact definition of what? The resolving power of what is grating is. Okay. So let us discuss. So the resolving power of grating, that depends on what factors. So how that two closely spectral lines are just resolved. And one more thing. So here you are getting a religious criteria, so that which you have already learned in second PUC. So that I will tell you. So here, what is the condition for just resolutions for our religious criteria? Okay. Here that's AP is my plane transmission grating, so in which it contains in what n number of lines are ruled over that grating surfaces. Okay, when you are having n number of lines are ruled over that grating surface, the grating elements, so I'll think you know that each opaque portion is having a distance of b, and transparent portion is designated by a symbol of what is A. That A plus B will give you the what? The grating constant or the grating element. So that is also called it by what is grating spacing. Okay. So therefore, the length of your grating, that's AB is equals to, so have written what? Capital N into bracket what? Small a plus what it is B. A plus B it is. Okay. Suppose so here, a plane wavefront, when it is incident on that your grating element AB, that a beam of light contains two spectral lines. What is that? Incident a beam of light contains what? Two spectral lines of wavelength. One is lambda and another one is what? Lambda plus d lambda. Okay. For the wavelengths, for the light, for the spectral lines which is having a wavelength lambda, so on incidenting that your what? A plane transmission grating, it gets diffracted. It is diffracted along these directions. So by making an angle of what it is theta. So after diffractions, again it takes refractions to the your telescope of the objectives and forms an image on the screen at the point of what it is P. Okay. So this is for the what? The wavelength lambda. Okay. So next, so that what is the diffracted spectral lines. So having an angle of diffraction is what? Theta, forms an image at the point of what is P on passing to the what? the telescope of what is objectives. So these images are formed on the screen at the focal plane of our what telescope it is, okay, of the objectives of the telescope it is. So whereas that another wavefront, so which is having a wavelength of what is lambda plus d lambda, so forms an image at the point of what it is q. So on passing to the what telescope it is. So this a spectral line, so which is having a wavelength of what lambda plus d lambda, gets diffracted. So by making an angle of what d theta with your what first line, or to the total diffractions is what is theta plus d theta. It's okay. Here, so we are our work is to what view those two lines are what when they are just resolved. How that grating element splits those two your spectral lines. They are what just when you say that those two spectral lines are what just resolved. So for that, so what we are doing is, so draw a what perpendicular line AD to the your what wavefront BE. Draw a what AD perpendicular to your what BE. Then so you are getting an angle triangle. That's what ABD or ADB. So in these triangles, the cos of theta is equals to base divided by hypotenuse. So that's why. So you are reading what it is AD. What it is cos theta is equals to AD divided by what is AB. So therefore AD is equals to A plus B into cos theta. So let's call so this one as what second equations. Okay. So here AD is equals to what it is when you are drawing, but AD is equals to what AB into cos theta. But here the value of your AB, what it is AB is equals to what it is n into capital N into it's what A plus B. So that you got what, so inside here. So that's you got what, so inside here. What I am telling is, so you have drawn what AD perpendicular to what your BE. Then from this triangle cos of theta is equals to, so it is what, so AD divided by it is what AB. So therefore make it cross multiplications. We require what AD is equals to what AB cos theta, but AB is nothing but what the length of our grating. So therefore the length of our grating is what it is just it is what n into bracket what is A plus B into cos theta. Okay. So let's this one. So you make it what a second equations. As you know that for an nth order spectra for an place transmission grating, so it is given by what is A plus B sin theta is equals to what n lambda. So when n is equals to what 0, 1, 2, 3 and so on, so which you are calling it as what order of spectrometers. Okay. So this one, so you want to differentiate with respect to what it is theta and lambda. So that your above equation becomes what A plus B cos theta into d theta, that's equals to n into d lambda. Okay, and make it class specifications. So d theta is equals to small into d lambda, that's divided by what A plus B cos of theta. Okay. So these two your spectral lines, whatever the spectral lines which are having a wavelength lambda and lambda plus d lambda. So when do you say that these two lines are what just resolved according to the resolution criteria, according to your what resolution criteria. So these two your spectral lines are what just resolved. So see here, these two what spectral lines are just resolved when the central maximum of what one, this is central maximum of what one diffracted line is what coincides with what the coincides what the first minimum of the other diffracted line of a wavelength is. So what it is, the two spectral lines are what just resolved if the central maximum of a diffracted line of wavelength lambda is coincides with your what the first minimum of your what is the first minimum of what the diffracted spectral line of wavelength lambda plus d lambda. So in such situations, in such cases, the two spectral lines are what? Just resolved. Okay, so that is the condition for your just resolutions according to your religious criteria. So we know that for angular limit of resolutions of the telescope objectives, the angular resolution of the our telescope objectives, limit of resolution of the telescope objective is given by a quantity. So d theta is equals to lambda divided by small d, where that small d is nothing but what? That width of the your emergent wavefront, or you can call it, that is also what? The diameter of our telescope is. Okay, so therefore this small d is nothing but what? It's AD, it's there is nothing but what? The width of the our wavefront is, or you can call it what? The diameter of the wavefront. So that your our equation becomes d theta is equals to lambda divided by what is a into d, because AD is what? Small d. But the value of your AD, so from equation number it is what? 2. AD is equals to what? Capital N into bracket a plus b cos theta is there. So that you want to what? Insert here. So therefore your equation becomes lambda divided by what? N into bracket a plus b into cos of theta. Now you want to equate equations 4 and what it is 3. It's, so you are getting n d lambda divided by a plus b cos theta equals to lambda divided by capital N into a plus b into cos theta. You make it cancel, so these two terms. So the remaining quantity you are getting what? Lambda divided by d lambda is equals to small n into capital N. So lambda divided by d lambda measures what? The resolving power of your grating. So that resolving power of our grating is mainly depends on what? The order of the spectrum, that's small n, and it also depends on what? Capital N, which is nothing but what? The number of lines ruled on the grating element. So this is the descriptions regarding your what? The resolving power of the grating is. Okay, so very interesting, and just remember these two steps, nothing in it is. Okay, with this whatever the syllabus mentioned in Fraunhofer diffraction is completed. So in our next class we will discuss another concept, another chapter, so which is nothing but your what? Polarizations. Okay, thank you.